Okay, so up to here we are doing some exercises related to normal distribution, but we are going to do more advanced exercise. Up to here I give you I ask you to calculate some probability, but I will go the other way. I will tell you the probability, then find the value that gives you the probability equal to what I say. Okay, that is actually the idea of percentile, right? So remember, the percentile is the ranking of the outcomes. Like 99 percentile is the top 1% outcome. So 99% is below that outcome. And like say 50 percentile is in the middle, median. 25 percentile is the value that is bottom 25% point. Okay? So in other words, you can write it this way. So suppose that like the probability smaller than A is P, say 25%. If P is 25%, then we say A is 25 percentile, right? So this is the definition of percentile. And because this is the CDF, you may write it this way. And what I'm going to do is I am curious about P percentile of the distribution. What is A? Right? So that is going the inverse. We need to use the inverse of this function. And of course, Excel has the built-in function, right? I will do this so I said we are going to use this function norm.s.inv, that is inverse function of normal distribution. So let me go to here. So I will think about different percent, like say 5 percentile, that is 0.05, 0.1, 10 percentile. And let's start from 1%. And like 25%, 50%, 75%, say 90%, 95%, 99%. So I am going to calculate the standard normal distributions percentiles at these percents, right? How do I do that? Norm.s.inv, and just enter this probability. I will refer to that thing. Then just you enter like that. Then it returns the value so this means the CDF at minus 2.3263 equals 0.01. This is the meaning of this result. Okay, the CDF at this point equals this probability. I'm telling you the probability first, and then I calculate the percentiles. I will drag. Then you can get the percentiles at different points. Okay. So what is interesting here is bottom 1%. This is actually bottom 1% value, right? Bottom 1% value and top 1% value are symmetric due to the symmetry. And of course, the median is 0. That is the center. The mean equals the median because everything is symmetric. And this was first quartile, and third quartile. We learned the interquartile range. That is based on these two guys, and they are also symmetric, right? I don't know why there is additional decimal place. Right, anyhow, you can see they are the same thing. Oh, and this is bottom 5%, bottom 10%. And this is top 10% and top 5%, like that. So their percentile values increase as you increase this probability, because this is the probability. Those values should the percentage is the probability below those values. So as the percentage increases, you have to increase the bar further. So it increases and they are symmetric. And you are going to see those numbers pretty often. I tell you, uh, keep those values in mind. And just to add one more, what's more important is bottom 2.5%. This will be often used. And if you have taken another statistics course, I guess this number should be familiar to you, right? And 2.5%, top 2.5%, needless to say, it should be positive 1.96, but just let me complete this. So these numbers are the most common numbers you are going to use in later analysis. So we found those values, and just practice. What is the top 10% value? Top 10% means 90 percentile. Like if you count probability from the top, we call this top 10%, but percentile is based on cumulative probability, so it counts from the bottom, so we have to use 90. So the answer is C, right? 10% from the top or 90% from the bottom. They are the same thing, right? Anyhow, it is approximately 1.28. Okay? And notation later we are going to use is like this. So it's a little bit tricky. We use alpha as subscript to find this value. So z lowercase z subscript alpha denotes the value that is top alpha probability, right? So in this notation, alpha is probability counting from the top. That's kind of, I don't like this notation, but it is the convention. I cannot change the notation, even if it is like inconsistent. I have to follow that, and you have to follow that. So for example, lowercase z point subscript 0.1 is top 10% value of the standard normal distribution, right? So this notation is later commonly used to find this, to denote this probability, to find this value that satisfies this probability. Okay. Then, in other words, using the CDF of z subscript alpha equals 1 minus alpha. So alpha is not cumulative probability. Then, based on these percentiles, what is the value z subscript 0.05, which means top 5% value, which is 95 percentile. So it is D. So don't be confused. It's very confusing, I understand, but so you should not. Okay. So this is the answer. By the symmetry, like we usually think about top alpha value. The bottom values are just minus of that, right? So bottom 5% value is denoted as the minus z subscript 0.05. Okay? Then most common use of this notation is like this. Top 5% value is z.05, bottom is minus z.05. So that means if you drop bottom 5%, top 5%, then middle 90% lies between plus minus z.05, like this. So this is the common notation, common method we are going to use in the future, right? So if you are interested in the probability, middle probability of 1 minus alpha, say 90%, then alpha is 10%. Then you have to drop 5% from the top and 5% from the bottom. So you have to find half of the 10%. So you are looking for z alpha over 2. That is the probability you lose from the top and probability lose from the bottom. Okay? So we usually think about plus minus z alpha over 2 containing 1 minus alpha. You get it? So it's getting confusing, but just follow step by step. Z subscript alpha is top alpha value, and then we are dropping the tail probability alpha from the top, but we actually wanted to start from the middle probability. If you start from the what I want is, I am curious what is the plus minus value that contains 90%, then you have to find these guys, right? So later we will repeat this exercise, so you have a chance to recap this. So far we studied only the standard normal distribution because that is simpler, but that's also pretty general. We may generalize the standard normal distribution to any normal distribution. To do that, you have to review. I have to remind you of the linear transformation formulas, right? So remember, if you transform x to y by a linear relationship, linear transformation, then their mean and variance change like these, right? Mean, variance, standard deviation. Mean is easy, but the variance is multiplied by a squared, the multiplication squared. Standard deviation is just multiplied with the same constant, but the addition or subtraction does not affect variance or standard deviation. How do we use it? We are going to use a linear transformation to make any normal distribution to standard normal distribution, like this. So suppose that x is normal distribution, and then y is also normal distribution. Actually, this is amazing property for normal distribution. Well, I'm not going to prove it, but think about any other properties. Like, so if you multiply something and add something, the shape of the distribution will be totally different. Binomial distribution does not satisfy this property. Most of the distributions do not satisfy this property, but normal distribution does. Anyhow, so if x is normal distribution with parameter mu and sigma squared, then the new distribution y, new random variable y, will have these mean and variance. Mean will be a mu plus b, variance will be a squared sigma squared, right? It's pretty straightforward. Then as a result, we know the mean and variance of y, and additionally we know that y is normal distribution. That is another property of normal distribution. So anyhow, we know everything about everything about y. The distribution of y is perfectly described by normal distribution with its parameters. And a special case we want is the new random variable. I want the new random variable to be standard. That means mean is 0, standard, like the variance is 1. When this is satisfied, and it is easy to see that when you multiply 1 over sigma, so in here, when you transform like this, a and b, you may choose a and b, but if you designate a as 1 over sigma and b as minus mu over sigma, if you plug them into this transformation, it is easy to see that y is x minus mu over sigma. This is standardization. We learned this standardization method in chapter 4, right? And that means no matter what x is, like no matter what parameter x has, after this transformation y is always standard, mean 0, variance 1, right? So we promise to denote that as z. So whenever you have a normal distribution, if you standardize the normal distribution this way, the result is standard normal distribution. And we know how to handle standard normal distribution. Okay? And it also has its own interpretation. The standardization captures how many standard deviations you deviate from its mean, right? If z is plus 1, that means the x value is 1 standard deviation greater than its mean. If z is minus 2, that means the x value is 2 standard deviation below the mean. Like that, z is pretty informative, right? As x increases, z also increases, and if x is above its mean, then z is positive and z is negative. So standardized variable itself is pretty useful, but it's also useful by applying the normal distribution, standard normal distribution. Okay? So then how do we use it? We may use the standard normal distribution to calculate any probability at the CDF, the cumulative probability for the non-standard normal distribution. X is non-standard, but we may use the standard normal distribution to calculate the probability. Think about this. Suppose that you'd like to calculate probability below A, right? And X is non-standard, but we can standardize both sides. We are going to standardize X, but at the same time, within the parenthesis, you need to maintain the inequality, so you have to do the same transformation on the other side. So when you transform X like this, you must transform A with the same transformation so that the inequality does not change. Okay? Right? And in this way, we know that the left-hand side of the inequality is standard variable z. The right-hand side is what you need to calculate. Okay? And then you can find this probability from Excel, right? Because z is standard normal distribution, right? It is standard normal distribution cumulative probability. So it should be pretty powerful because any normal distribution can be converted into standard normal distribution. So that's what you need. You just need to know standard normal distribution, right? The point here is a lot of students make a mistake in this step. You have to standardize both sides because the inequality should not change. Okay? Here is an example. I'm going to think about a tire, like for tire for vehicles. Let X be the life of a tire in mileage, how much miles a tire can endure. And we assume that it is normally distributed with mean 35,000 and standard deviation. This is not variance, this is standard deviation 5,000. So it is definitely not not standard. Mean and variance are not 0 and 1. But we would like to calculate the probability that this a randomly chosen tire wears out before 40,000 miles. It does not last 40,000 miles. How can we calculate this probability? Right? So follow the steps. Standardize X, but at the same time you have to standardize all the accompanying terms like size. 40, like the counterparts of X is 40,000. When you standardize X, you have to standardize 40,000. Think about this. X is like several thousand. But after standardization, it will be like 1 or 2. It will be between like 1 and 2. So 40,000 must change its scale units to match the standardized variable. So you do this. Subtract the mean, divide by the standard deviation. Actually, you don't need to plug in those numbers on the left hand side because anyhow you know it is standard normal distribution, right? In the end, it is just standard normal distribution, so you don't need to do any manipulation here because we know it's standard normal. But the right hand side need some algebra. Subtract 35,000, the mean, and divide by the standard deviation. And then it is 1, right? So then the complicated cumulative probability becomes a cumulative probability for a standard normal distribution, which we know how to calculate on Excel. We calculated that. This is the cumulative probability. Okay? So this is probability z smaller than 1. So that's the answer. That is the answer to this question. Right? So again, the point here is we are interested in a probability that is very like large mean and variance, but does not matter. We may scale them back to our standard case and use Excel. That's all. So I will have you do this question by yourself. Use Excel, open Excel, or online standard normal calculator and standardize the non-standard normal distribution and calculate this probability. Pretty much the same structure. Okay, try this, finish this algebra before starting the next video. See you there. Bye.